In 7.1, we left off where we were trying to find the sample size necessary to minimize the margin of error. And there are two different formulas that we use, and this depends on whether or not we know what p hat is, or the sample proportion. Now, in order to actually know what the sample proportion is, this usually comes from either another study or maybe just a rough guess of what you think it could be. In the homework and also in the exam, if this shows up on the exam, the p hat will actually be given to you, so you won't have to actually make your own educated guess on it. One thing that's really important to note with this, with either formula, is that the sample size, you have to round it up. So the point of rounding up the sample size is you want to minimize the margin of error. So the larger the sample size is, the smaller the margin of error gets. If you were to round down, you end up with a larger margin of error than what we would have liked to have in the problem. So looking at this example, eBay is trying to determine the current percentage of US adults who now use the internet, which of course can be very beneficial for the company if they know what their audience is. So we want to use this result from a Pew Research Center poll that 73% of US adults use the internet. Now, this is for a 95% confidence interval. Remember that that means that if we were to draw out the normal distribution curve, the middle area is the 95%. So that means that either tail has 2.5%, meaning we want the z-score that has an area of 2.5% to the right of it. In the table, we can look for the area that has an area of 0.025 to the left of it, and that would give us the negative z-score. Or we can find the complement and take 1 minus 0.025 to get 0.975. The z-score that gives us an area of 0.975 to the left of it is 1.96. So in our formula, we have n is equal to 1.96 squared times 0.73 times the complement of that, which is 0.27. And we divide all that by the margin of error squared. So we want the error to be no larger than 3 percent points. So we have 0.03 squared on the denominator. Plugging this into the calculator, and we end up with 841.3104. And so, of course, we have to round up to 842, because we need to have at least 841.3104 for a sample size. And of course, our sample size must be a whole number, so we have to round it up to 842. For the second problem, we're going to assume that we have no prior knowledge suggesting a possible value of the proportion. So that means that we're going to have to replace 0.73 and 0.27. We're going to replace that product with 0.25. Doing this calculation, and we end up with 1067.11 repeating. And when we round this up, we end up with 1068. So that's all we have for 7.1. Now we can go ahead and move on to 7.2. So in 7.2, we are still going to be making confidence intervals. However, we're going to be looking at the population mean instead of the population proportion. So a lot of this will be very similar in the fact that we are still going to find the margin of error. We are still using the formula for the confidence level as 1 minus alpha. And we're still going to be basing our margin of error formula based off of the z-score formula. However, if we look at this formula, if we're trying to estimate the population mean, how do we know what the population standard deviation is? If you recall, the standard deviation uses the mean in order to calculate it. One way you can calculate the standard deviation is if you already had this from another study. However, this usually is never the case. So for this class, we're only going to be testing you based off of the case where sigma is unknown. Well, similar to how we would be using x bar, or the sample mean, to estimate the population mean, we're also going to use the sample standard deviation s to estimate the population standard deviation sigma. However, this does introduce some more error, so we do not actually know how good the sample standard deviation is as an approximation for the population standard deviation. So we need to overcompensate the width of our confidence interval for our lack of knowledge of how good S is. And to do this, we're going to use the student t distribution. Now, the student t distribution has some similarities with the standard normal distribution. However, the biggest difference is the degrees of freedom. So this slide just has a few properties of the t distribution. It is still a density curve. The area under the curve equals 1. It goes from negative infinity to positive infinity. It is also symmetric, similar to the standard normal distribution. But what's different is the degrees of freedom. And the degrees of freedom is the number of sample values that can vary after a certain restriction has been imposed on all data values. So for the degrees of freedom in this section, the degrees of freedom will end up being n minus 1. To find a t value, we can do this in one of two different ways. We can use the student t distribution table, that is another handout that you can find in my math lab, and it looks something like this. Or you can also use Excel, which has the inverse t value. So in this problem, we want to find the value that has an area of 0.05 to the right of it with the degrees of freedom of 13. So in this table, we have the area in one tail, and in this case, the area was 0.05. So we're going to be looking at the fourth column here. And we keep going down until we find the degrees of freedom being 13. So the answer in this case is 1.771. So how we do this with Excel is we type in 0.05 into the area. Degrees of freedom is 13. And notice that this actually gives us the negative value. By default, this is finding the area to the left of the value. So if we actually want to get the correct value, you would type in 0.95, since that is the area to the left of that t value. Now notice that this just changes the sign from a negative to a positive. So as long as we just know that we need the positive answer, we could just type in 0.05 instead. So moving on, we need to first look at the assumptions that we need for a confidence interval. And essentially we need to have a simple random sample. We need to be able to use the central limit theorem, which can involve using the normal probability plot to determine if this is in fact a normal distribution. And we also have to verify that there are no outliers. And we're assuming that sigma is unknown. So now we have the formula for the confidence interval and the margin of error. So the formula for the margin of error takes the critical value times the standard deviation for the sample mean. And we take that margin of error and we subtract that by the sample mean. Now, this note on the bottom is just in case you happen to use statistics for another class where they do look at the case where sigma is known. The only difference is that we use sigma instead of S, and because we don't need to overestimate the confidence interval, we would actually use the z-score instead of the t value. So looking at example 2, we have some data points, and we are actually given the summary statistics for the data points here. And we're looking at hectograms of randomly selected girls at birth. And we want to construct a 95% confidence interval for the mean birth weight of girls. Now, if we were to check all of our assumptions, the one that I would be a little bit worried about is, are these from a normal distribution? Because clearly we do not have a large enough sample size to verify the central limit theorem. According to our normal probability plot, it does look like they follow a somewhat linear pattern. So I can safely assume that this is a normal distribution. And of course, since it does not tell us that sigma is known or unknown, we can safely assume that it is in fact unknown. And we can continue on by calculating the margin of error. So before we actually do the margin of error, we need to figure out what our critical value is. Now, since this is a 95% confidence interval, that means the middle area is 0.95, so each tail has 0.025. And I know my degrees of freedom is just the number of data value points, which is 15, minus 1, which is 14. So if I look this up in the table, we have the area in one tail is in this middle column of 0.025. And we go all the way down to this row of degrees of freedom 14, we get the t value of 2.145. So now the margin of error is equal to 2.145 times the sample standard deviation, which is 2.9, and we divide that by the square root of 15. And we get the margin of error to become 1.606. So if we take x bar minus the margin of error, we get 29.294. And then if we take x bar plus the margin of error, we get 32.506. So this gives us our confidence interval of 29.294 and 32.506. So in conclusion, we are 95% confident the true mean birth weight of girls is between 29.294 hectograms and 32.506 hectograms. Now, of course, we can also do this on the calculator or in Excel. So in Excel, we would end up using the t-interval. So in Excel, we would simply type in our data set on the left, and we would type in the confidence level of 0.95. And in this case, I rounded it to 3 decimal places. And notice that we'll get something pretty similar. The reason why it's a little different is because our mean and standard deviation is a little different from the rounded version that they had. If they give us the statistics, which in this case they did, we can type those in instead. So we'd have 30.9, 2.9, and then 15. And we can still type in the same confidence level and decimal places. Notice that this is closer to what our answer was because we based ours off of our statistics. So in this last example, we have the annual chicken consumption in pounds for 17 randomly selected people that is displayed in the table below. Now we want to find a 90% confidence interval for the year's mean chicken consumption mu. Now we did verify this clear back in section 6.5 that 0 ended up actually being an outlier, and we removed it by saying that we're only interested in the population of those that eat chicken. So when we remove this, this did end up being a normal distribution. So let's go ahead and type these values into our Excel spreadsheet. After typing in all the data values, I found that the confidence interval is between 62.256 and 71.994 pounds of chicken per year. So in this case, we have our confidence interval of 62.256 and 71.994. So in conclusion, we are 90% confident the true mean annual chicken consumption is between 62.256 pounds and 71.994 pounds. Thank you for watching, and I'll see you in the next video.